All right, I guess we'll go ahead and get started. We got a little bit of stuff to cover today, and so we need to get moving on. And anybody who's late will have to catch up. Let's see. I don't remember if I have a video to play or not. I'm gonna share it like I think there is a video, so I need to share it in the right way to be able to show that video. Okay, first hour 0B. There we are, 0B. All right, make sure I'm going to the right class. Fake student has not done his work. Look, he's got a 33% in the class. He's got to get his work turned in. He did well on getting that in, but didn't turn in what was due Sunday. So those 2 zeros are bringing his grade down. But let's see. Looking at this. This should not be there. We're not doing 5.06. I want to take that out. I took it out of the other Algebra 3 class. It didn't come out of this one. But we're doing 5.04 and 5.08. We're going to do geometric series and graphing geometric sequences and series and arithmetic sequences and series. We are not doing sigma notation. It's not necessary. We're going to skip that. So we only have 2 assignments, not 3, as you see on the screen there. So 5.04. I may leave sigma notation on there for a day or two if anybody wants to just look at it, but we're not going to cover that. Geometric series lesson. So we've looked at arithmetic series. We've looked at arithmetic sequences. We've looked at geometric sequences. Oh, that's right. There is this little video. I like watching their goofy little cartoon videos for some reason. It just amuses me. But we're going to watch this little video they have here. It's like 2 minutes and 41 seconds. And it's going to talk about, well, you'll see. Here, make it big.
Rachel's mother just returned from a vacation to Moscow. She brought back a set of matryoshka, or nesting dolls, for Rachel. Nesting dolls are a series of dolls that open up so that each doll contains a smaller doll until you get to the smallest, innermost doll. The packaging that came with the dolls notes that there are 8 dolls and each doll is 10% smaller than the previous one. Rachel has a 2-foot-long shelf in her room, but it's covered in small dolls already. She doesn't want to clear it unless she knows the nesting dolls will fit. First, she measures the largest doll. At its widest, it is 5 inches long. Rachel does not want to find 90% of 5 inches, then 90% of that number, and so on 8 times over. So instead, she uses a special way of adding numbers that change by a constant percent. The first doll is 5 inches wide. The next doll is 5 inches times 0.9 because it is 10% smaller. The next doll is 5 inches times 0.9 squared because it is 10% smaller than the previous doll. Rachel can find all of the doll's widths this way. She knows that when a number is multiplied repeatedly by the same constant, the sequence of products is called a geometric sequence. In this lesson, you will see how to add terms quickly in a geometric sequence. This sum is called a geometric series. You can use it to see if the nesting dolls will fit on Rachel's shelf. You find the sum of a geometric series using the formula S sub n equals a sub 1 minus a sub n times r all over 1 minus r. S sub n is the sum up to the nth term. In this case, you want 8 terms added. A sub 1 is the first term, and a sub n is the last term. So here, a sub 1 is 5, and a sub n is 5 times 0.9 to the 7th power. R stands for the common ratio, and is the factor that each term is multiplied by. In this case, r is 0.9. So substitute and solve. The dolls will span about 28.5 inches, or just over 2 feet and 4 inches. Rachel's 2-foot shelf is not enough.
All right, so if Rachel had any spatial sense, she would realize that she can just take that last little doll and put it in front of the ones next to it because they're not taking up the whole shelf front to back. They could just push it back a little bit, put the little one right in front of them, and it'd be fine. But I appreciate Rachel's dedication to mathematics to figure out how lazy to be there, because she doesn't want to clear the shelf unless they'll fit. So, but it did show us something about a geometric series there, adding them all up. Gave us our first equation for that. So let's look at this. So just like when we talked about an arithmetic sequence and arithmetic series, we need to know which one we're dealing with so we know which formula to use. We already have the formula for geometric sequences because we did that last week. But how do we know if it's a sequence or a series? Well, remember, a series is when we add them all together. A sequence is just a sequence of numbers. All right, we got a whole group of numbers that go in order with some common ratio or common difference if it's arithmetic. But if it's a series, we're adding them all together. So if we look at this list of numbers, we have 1, 5, 25. Well, that is a geometric sequence. It's being multiplied by 5 each time, and it's not adding them together. It's just giving us the list of numbers. So that would go up in the sequence. Here's another list of numbers: 4, negative 32, positive 256. It's multiplying by negative 8 every time. 4 times negative 8, negative 32 times negative 8. Negative times a negative makes that one a positive. That's also just a sequence of numbers. But this one, 3 plus 6 plus 12, it is multiplying by 2 every time, but we're adding them together. So we get to use a geometric series formula for that. And these are also adding together, even though you're like, oh, that's a subtraction. Yeah, it's adding a negative number, but it's multiplying by negative 3. So we're still combining them all. We're adding negative 27 to 9 and adding 81 to that. So that is also a series. So just being able to recognize so that we know, is this a sequence formula or a series formula? All right. Oh, and now they want us to match terms. This is also important. This is our vocabulary that we're using. We have to know the proper vocabulary to know how to use our formulas. So here's our 5 choices: the first number in the sequence, the common ratio between the terms, the sum total of the numbers in the sequence, the number of terms in the sequence, or the value of the nth term in the sequence. And the first thing we have down here, you see down at the bottom, a sub n. A sub n. Is that the first number in the sequence? No, a sub n is not the first number in the sequence. It's not the sum. If it's the sum, remember it's an s sub n. S sub n is the sum. A sub n, is that the number of terms? No, that's not the number of terms. Is that the common ratio? It's definitely not the common ratio. That must be the value of the nth term. A sub n. So if n is 8, then that's the 8th term, a sub 8. So we'll put those together. A sub 1. That one, if we remember from last time, is the first number in the sequence. We call it a sub 1. That's how we label it. That's the name. N is just the number of terms in our sequence. R, there's that common ratio. If it was a D, it'd be common difference. That was arithmetic. But geometric uses R for ratio. And there's that S sub n. It says that's the total sum. So it's important to understand the terminology that we're using so that you know exactly what we're talking about when we use these phrases. All right, so if you need to go back and do this yourself, just to make sure you know that, this is right here on page 1 in our lesson. So you have access to that. They got a lot on page 1 this week. Usually page 1 doesn't have very much, but we have a lot. All right, so we have, let's find the formula for finding the sum of a geometric series, which they gave us that in that first video, but this may be the other formula. There's 2 formulas. So if we have this, 3 plus 6 plus 12 plus 24 plus 48 plus 96, all right, that's 6 terms sequence that is multiplying by 2 each time. It says, what is the first term of the series? Well, all we have to do is go to the beginning and see what the first term is. It's obviously a 3. Look, check our answer, 3. The great thing about these lessons has lots of this where you can do the work and then check your answer. What is the common ratio of this series? Well, if the sequence is 3, 6, 12, 24, 48, the common ratio must be a 2, right? Because that's what it's multiplying by. Multiplies by 2. So we check that. The common ratio of the series is 2, which is found by dividing any term by the preceding. Yeah, if you wasn't sure, you could go to the last term and divide it by the one in front of it. 96 divided by 48. Or we could go to the 48 and divide by the 24 in front of that. But you can pick any term, 6, and divide by 3, and that's 2. So any term that you pick, if you divide by the one in front of it, that'll give you the common ratio of 2 in this case. So it says, what is the sum of the series? Well, we could add them up. 3 plus 6 plus 12 plus 24 plus 48 plus 96. Let's see what they do. 189. So we can just put them in the calculator, add them up, and we get 189 is the answer. So this isn't so bad because we just have 6 numbers, and they're not like crazy numbers. But what if we want a 61 term sequence added up? All right, so some of them are not quite so simple. So let's use this simple sequence here and see if we can't come up with a good equation for that. So we're going to watch this video, which is 2 minutes, 11 seconds. Let me make that bigger. Factor of 3 out of each term. We're not going to have sound on this one. I guess we have sound on it. So we factor a 3 out of each term. They're all divisible by 3. The common ratio is the 2, so let's write each of those leftover things as a factor of 2. We got 3, and then 3 times 2, and then 3 times 2 squared, and 3 times 2 to the third, and 3 times 2 to the fourth, 3 times 2 to the fifth. So to find the formula, each term will just need to be written using variables. So we'll take the 3 and replace it with A1 every time you see that 3, and we'll take the 2 and replace it with R. Multiply both sides of the equation by the common ratio. So if we multiply both sides, some S8 times R and all those other times R, that changes it to the last term being R to the 6th. Oh, that's an S to the 6R. Subtracting the equation S6 from S6R gets even closer. But now they're getting fancy with it. They're going to subtract that entire thing. And look, they offset each other to where it just leaves the first term and the last term. A1 minus A1 times R to the 6th. So factor the S to the 6th out. 1 minus R. And divide both sides by that. That'll give us our formula. So that's a mathematical way to come up with the same formula that they gave us in the first video. A1 minus A1 times the ratio to the 6th power, because 6 is the number we were going for. So in our notes, this is our first equation we should have to find a geometric series. We saw it in the first video. The second video showed how you can derive that using the information that we had. So you have the sum of n terms, the first however many terms we're taking of this sequence, is the first term minus, oh, they came up with a different one. No, a sub n, right? A sub n. So if this is the first 6 terms, that would be the 6th value times the ratio divided by 1 minus the ratio. I'm like, okay. Well, let's try that with the one that we already know the answer to. So we had the sequence that was 3, 6, 12, 24, 48, 96. And we already know they added up to 189 because that was earlier in the lesson. But let's use this formula and see if this formula works, because we haven't done it with this formula. So there's 6 terms. So the sum of the first 6 terms A1, so the first term, which is 3, minus A sub n, which A sub 6 is 96, times our common ratio. Well, our ratio is 2 because it's multiplying by 2 every time. All over 1 minus the ratio again. Okay, well, the bottom, we already see 1 minus 2 is negative 1. And we got 3 minus something, 96 times 2. Most of you probably have that in your head, but we're going to put it in the calculator just to make sure we're not making any mistakes. 96 times 2. 192. So 3 minus 192. Well, that's going to be negative 189. Because we've got a positive 3 and a negative 192. Divided by negative 1. So a negative divided by a negative. 189 divided by 1. The formula does come up with the same answer as just taking those and adding them together. So this formula does work. We've looked at it with an actual example and come up with that. So it might be good to have an example with your formula just so you know how to use the formula. Because if you don't know what A1, A sub n, all those things are, you will struggle to get the right answer. You have to know how to use your formula. So it's always good to have examples written down with any formula that you learn. All right, let's go back and see what else this lesson holds. When given a geometric sequence with a set number of terms, it's possible to use a geometric series formula to find them. So here they're going to give us some more examples. This is 5, negative 15, 45, if there are 11 terms. All right, so let's go ahead and work that on paper just to give us another example where we're trying this out. So it's 5, negative 15, positive 45, 11 terms. All right, so if we have this sequence, 5, negative 15, 45, and there's 11 terms, we have to find, first off, our R. We need to know what the common ratio is. So we can take any two terms that are together and divide the second term by the first one. So let's just use negative 15 and divide it by 5 as a ratio, divided by underneath, or you can do, you can do that with the negative 15 and the 5. But negative 15 over 5 is negative 3. So this is a common ratio of negative 3. When you take negative 15 and multiply it by negative 3, you get a positive 45. So our R is negative 3. All right, let's use our formula and see if we can come up with what the total would be for the first 11 terms. We only have 3 terms. So this is going to give us some problems because we don't have the 11th term, right? We don't have the 11th term. So what do they show us on that? There's a different formula. So this will be the other formula we write in our notes right here. So we're going to write S sub n equals A sub 1 minus A sub 1 R raised to the nth power. It's very similar to the first formula we have. So we're going to put this in our notes. S sub n equals first term minus the first term times the ratio raised to the power of n over 1 minus r. So very similar to the other equation we were already had. The only difference is this one uses a sub n times r. This uses the first term times r to the power of n. Okay, so that one we can do because we only have to have the first term in the ratio. That's all we have to have for this formula. This one we have to have the first term and the last term in the ratio. So let's try this. Here's our sequence. So S sub 11, because we want the first 11 terms, equals A sub 1. A sub 1 is 5 minus A sub 1 again, 5, times R to the n, negative 3 to the 11th. All right, because that's what our ratio is, and n is our number of terms. We want first 11. 1 minus R. 1 minus the R is negative 3. So I'm going to write it like that just to remind ourselves we're subtracting a negative. Okay, so the bottom, 1 minus negative 3, that's a 4. Up here we have 5 minus, and we have to calculate what 5 times negative 3 to the 11th is. So we'll need our calculator back for that. So let's take 5 times negative 3 to the 11th. So 5 times, we'll put negative 3 raised to the power of 11. The 5 times negative 3 raised to the power of 11 is a big number. That is negative 8,85735. Okay, let's move this. Had to make our line bigger. 5 minus that. Okay, again, we're subtracting a negative, which means we're just going to add these together. So if we add those and subtract a negative, it's 8, 8, 5, 7. 5 plus 35 is 40. Divided by 4. So let's pull up our calculator once more. 8,85740 divided by 4. So if we add the first 11 numbers of this sequence, 221,435. If anybody wants to test that for us, please do. But you have to figure out what all 11 terms are when you're multiplying by negative 3. And obviously, it gets really big. Let's see if they get the same answer. 221,435. Oh, not the right screen. There we go. There it is, 221,435. 221,435. All right. Oh, lesson summary right here. There's more examples. Example 4, example 5. This is an application. A popular smartphone app increases the total amount of points to reach the next level. We're used to playing games like that where you get enough points. Each level, the points needed to move on doubles. So, right, the first level, okay, we get 10 points, we go to the second level. But the second level, now you got to get 20 points before you can go to the third level. Then you got to get 40 points to go to the next. So here's a little chart. See, the first level in this one, you got to have 5. Then the second level, you got to have 10. Third level, you got 20 points. Fourth level, you got 40 points. Fifth level, you have 80. To where finally, when you're level 7, you have to get 320 points to advance to level 8. So this is just a nice graph of that. So we can see the geometric sequence. Notice it looks like exponential, right? Because geometric is an exponential growth. All right, and he wants to find the total number of points to get to the maximum level 7. So if I'm starting from 0, how many points would I need? You got to add all those together. So it says work this out on your own paper and then check your work. Okay, so let's do that example real quick just to show you how you need to use these. This is how you need to use these lessons. You find these problems, you work the answer, and then you check. You check your answer. So I'm just going to write down the first few. And he wants to know 7th, to get the maximum the 7th level. So if we're starting with 5 for the first, then 10, then 20. That's the first 3 terms. I could have wrote down more terms if I want to. 40, I could write them all. But he wants to know for the 7th. So you could actually use either formula because we do have the 7th is 320. We do have that. So we can use either one. So this goes all the way to 7. A sub 7 is 320. All right, so that is the 7th term. So let's work it both ways just to check that then. The common ratio, 20 divided by 10, 10 divided by 5, r equals 2, which they told us it doubled. So let's try this one first. First 7 levels, if we have a sub 1 minus a sub 7 times the ratio over 1 minus the ratio. Okay, that's that top formula. 5 minus 320 times 2, we can do that in our head, 640. You just double each of the numbers, right? Over negative 1. So 5 minus 640 is negative 635 minus 1. So you need 635 points total. That'll get you all the way through 7. That'll get you to level 8, basically, at the beginning of level 8. That'll get you through the first 7 levels. So let's check it using this formula now. Let's say we didn't have all the numbers. We just have the first few. S sub 7, A1 minus A1 times R to the 7th. 2 to the 7th over 1 minus 2. Okay, 5 minus negative 1. What's the odds that this is going to come out to be 640, huh? Let's put it in our calculator and see. 5 times 2 to the 7th. 5 times 2 raised to the 7th power. Looky there. Didn't matter which formula we used, if we wanted to go with the 7th term or just the first term in the ratio. Either way, we get negative 635 divided by negative 1. 635 total points is how much you'd have at the end of level 7. So there you go. Nice example to show. You can solve this using either equation. Just remember you have to have the last term to use this one. This one you just need the first term in the ratio. But it works. Either one works. We should have got the same answer because we're dealing with the same data and the same question. All right. It's still the same video. We're going to watch the same video again. So maybe they used the other equation. Let's look at the lesson summary. All right. The lesson summary basically just gives us the 2 formulas. All right. It says geometric sequence is a sequence of numbers separated by a common ratio that's being added. And you can use either one of these formulas. So if you have both those formulas in your notes, you're good because you can use your notes on quizzes. You can use them on tests. You can use your notes all the time. So if you have those 2 in your notes, then you've done what you need for 5.04. All right, let's look at, again, there's that sigma notation lesson that we're not going to do. I'm going to take that off, but I'll leave it there for a day or so if you want to look at it. But it's just a different way of writing. Skip that. It's got some videos in it. Shows you how to do that too. Oh, there's what sigma notation looks like. Since we were there, let me show you that real quick. That's what he's got written on that board. That big E looking thing, that's sigma notation. It basically says n equals 1 and you go to 15. So it's just another way of writing a sequence thing. I'm skipping that. All right, graphing sequences in series. Graphing sequences. Let me share this the other way because I know we're going to need to switch back and forth to Desmos. So it needs to be able to do that. Okay, the graphing sequences in series lesson. All right, so we're going to learn what key features are unique to graphs of sequences in series, and how can the average rate of change be found using a discrete graph. All right, so let's check out page 2. Okay, when we learned about arithmetic and geometric sequences in series, we learned how the domains has specific restrictions. Remember what we said about the restrictions on the domains? We said the range could be anything, right? Because our sequence of numbers has positive numbers, like we had 5, negative 15, positive 45. You know, we can go either way, positive or negative. There's no restriction on the range. But as far as the domain, the x's, the first, the term numbers, we're restricted on term numbers. First of all, we don't have the 0th term. We don't have the negative third term in our sequence. We don't have the negative 11th term. We don't have the 2.6th term of our sequence, right? Domain is restricted to counting numbers. Integers starting with 1. Integers greater than or equal to 1. So let's see. The domain is restricted to all integers greater than or equal to 1 because we don't have a 0th term of a sequence, or we don't have a fraction. We don't have a 3.5 term of a sequence. So can't even have a 0th place. So that's the restriction. But the range does have little to no restrictions at all, unless, well, let me say it this way. The range can have restrictions based on the situation. If we said that there's a farmer that has chickens and every day he gets one more egg than he got the day before. So the first day he went out and got 2 eggs from his chickens. They weren't laying very much. The next day he got 3. The next day he got 4. It's arithmetic sequence, right? 3, 2, 3, 4, 5, 6, 7. But the range is restricted in that case. There's no way that the farmer would ever go out and collect negative 5 eggs. Or he would never go out and collect 7.5 eggs. So in that case, we're restricted to numbers greater than or equal to 0. Because he could go out and collect 0 eggs. It turns out he didn't in that case. He started with 2. So it'd be 2 or greater. And would be restricted to only integers, only counting numbers, because of the situation. Arithmetic sequences in general could be anything, negative infinity to infinity. But you may have a certain situation that this is being applied to that restricts you just because. So you just have to think it. That's common sense. Okay, yeah, common sense. If he's collecting eggs, I'm not going to have a 7.681 in my range. It has to be a whole number. It has to be a positive number. So things to think about. Use your head when you got a problem like that. All right, we're going to learn a new term today that you may not have heard before. Discrete. Discrete. Now, I'm not talking about being very private with our formulas here and not letting people know what we're doing. That's a different kind of discrete, and that's spelled D-I-S-C-R-E-E-T. That's being discrete. Okay, now be discreet about this. No, this is C-R-E-T-E, spelled a little different, and this is a math term, and it means that something only exists at a certain value, like these sequences. If our sequence is 2, 4, 6, 8, 10, it's not continuous. It doesn't include 2.1 and 3 and 3.5 and 3.75 and 3. It only includes 2 and then jumps to 4 and then jumps to 6. That's called a discrete. Let's take a look at the graphs of discrete versus continuous. With continuous, we would make a line and we connect all of our points because we have a value at 2.5. At 2.5, it exists right there on the graph. It exists everywhere on the graph. But on a discrete graph, we'd only do the points because there is no 2.5. There is no 3.3 term. It's only the 3rd and the 4th term and the 5th term and the 6th term. So discrete. So we're dealing a lot with discrete when we're talking sequences. So in graphing a sequence, it's important to note where it'll show up. You may want to graph them by hand, but you can do it with Desmos. So let's use Desmos here, and I will show you 2 ways to graph a discrete function. And we will start with, let's say we're going to use this function right here. All right, the 3, 6, 12, 24, 48, 96. So we're going to graph that. And we know it has to be a discrete graph. We're not connecting these points. This is a geometric sequence, 3, 6, 12, 28. All right. So there's 2 ways. The first way is if you have all the values, you can say, okay, I'm going to make a table. And the first term is 3, and the second term is 6, and the third term is 12, and the fourth term is 24, and the fifth term is 48. And the 6th term is 96. So look at that. It graphed a discrete graph. See that? If I keep zooming out, I'll get all. There's the 48. And that makes a nice discrete graph. It's like, wonderful. Look at that. Does it all for me. But what if I'm graphing 15 terms of a sequence and I don't want to have to calculate all 15 and make a table? Can Desmos do that for me? Actually, it can. All right, let's look at just a arithmetic sequence. And if we look at this arithmetic sequence and we come up with a formula for it, let's see, what did I do with my pencil? Well, I went over there. Let's say we have this arithmetic sequence that is just 1, 2, very simple, right? 1, 2, 3, 4, 5. So if we made a formula for that, it's just y equals x in this case, right? Because the first term would be 1, 1. Second term 2, 2. If we make it a table, it'd be 3, 3, because the first term is 1, second term is 2. So this is the simplest, right? We just make a y equals x. And I want to graph that on Desmos as a sequence, not the line. But if I say, okay, f of x equals x, that would be the continuous graph. But I'm going to turn that off. I don't want that. Now I'm going to say n equals, and I put this bracket. So now it said, oh, you're making a list. You're making a list. I say, okay. And it goes from 1, comma, dot, 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 all the way to capital N. All right, that's when I don't know how many terms. If I know how many terms, let's say I'm going to do the first 15 terms or 20 terms. So 1 to 20. I'm graphing from 1 to 20. The first 20 terms. I put 3 dots in between those two just to show that there's a bunch of numbers between there. And said, this is what I want you to graph. The term, the first term, right? Comma, I'm just putting a point on there. F of x. Or did I do that right? Let's see. 20. It says I made a mistake there. Too many variables. I don't know what to do with this. I just did this yesterday. Is it capital N? No, it's N, comma, f of x. If I did N2, it's that. If I do f of x, oh, it's not f of x, it's f of n. F of n. N and f of n, which means take whatever term it is and substitute it in for x. So if I graph this point, the point n f of n, it'll take my 20 different n's, 1 through 20, as the x value of my point, and the y value would be substituting that 1 through 20 into my equation. And look, there is the first 20 in that arithmetic sequence. Very nice. I didn't have to calculate what all 20 were. It's like, well, it'd be easy with this, but what if it's 1/2 x minus 6? All right. Well, there's the first 20 terms. I didn't have to calculate what the first 20 terms were and make a table. What if it's geometric? Let's put in a geometric one where we just used our geometric formula for a geometric sequence. I'll go back and show you what the formula was because this is from our last lesson. The geometric sequence. A1 times r to the n minus 1. So let's start with the sequence. Let's see. We had 1, 4, 16, 64. So that would be 1. So I don't need that. We just need r to the n minus 1. So let's do that. So if we said it's 1 times r to the parentheses x minus 1. Oh, not r. The r was 4. Here's that geometric sequence. Starts with 1, goes to 4. The third term is 16. The fourth term is 64. So you can see all the terms. And we did the first 20. So if we keep zooming out, there's going to be a lot more numbers way up higher. They get big really quick. The seventh term is 4,096. It gets big really fast. But we can zoom back in here. So we can do that on Desmos. Put the formula of your either arithmetic sequence or geometric sequence. Choose the number of terms you want, 1 through 20, 1 through 8, whatever it is. And then put these points. Now notice I turned this one off. That's the continuous. I turned that off. I said, don't graph that one for me because I don't need the continuous. Just graph the point. And you can turn the points on and off too. But see, so you want to turn the points on. Graph the point in, which means first term, and then f of n, whatever the first term calculates to be. N is 2, the second term calculates to be. So it just graphs those points. And you can have it labeled them for you. Just click that little label button, and there's your points. First term is 1, second term is 4, third term is 16. So Desmos very nicely can graph arithmetic and geometric sequences for us. 464. Oh, that's nice. All right, average rate of change. Let's talk about the average rate of change. So you may have a problem. Okay, let me be honest. You will have a problem. We won't say may. That gives you a sequence. Let's just use the one we graphed just now. 1, 4, 16, 64. And it may say, find average rate of change between x equals 2 and x equals 4. You will have problems like this. I know there's problems like this. It'll be on the test. It'll be on the assignment this week. Find the average rate of change. Okay, so what's that asking for? It's just asking for the slope between the second point and the fourth point. If we looked at it in a graph, it's like it wants to know the slope between 2, 4, and 4. If we connected those 2 points with a straight line, what would the slope be? For 2, 4, and 464. So we have a formula for that. It goes way back to Algebra 1. Our slope formula, where you subtract the two y values and divide them by the subtraction of the two x values. What are the y values? Well, when x equals 4, 1, 2, 3, 4, 64. That's y2. Minus y1. When x equals 2, 1, 2, that's what the y equals. We can look at it in our graph if we're confused that. Well, here's when x equals 4, the y value is 64. When x equals 2, the y value is 4. So we can look at it on the graph, or we can look at it on the sequence, 1, 2, 3, 4. Divided by x2, well, we said that was 4. It told us what the x's are, and x is 2. So 64 minus 4 is 60. 4 minus 2 is 2. So the average rate of change is 30. Between x equals 2 and x equals 4. That's not the average rate of change between x equals 3 and 4, because that's a lot steeper here. I'm going to change how this displays it to make it a little easier. So if we say this goes from negative 10 to positive 10. Take all those little minor things out of there. Kind of spread those out a bit. See, the slope between 2 and 4 is not as steep as 3 and 4. 3 and 4 is steeper. If we turn it on, we can see that. See, it gets steeper as it goes. So if we calculated, I'll do this. If we calculate between 3 and 4, between 64, 64 minus 16, and 4 minus 3, 64 minus 16 is 48 over 1. So the slope between x equals 3 and x equals 4 is 48. That's a lot steeper. So in a geometric sequence, the rate of change is going to be different between the 2 points, between any 2 points. With an arithmetic sequence, it should be the same because you're adding the same amount every time. The slope is consistent. The slope is consistent with arithmetic. But the average rate of change is going to be different in a geometric sequence depending on the 2 points you choose. So I guess this should be in your notes if you don't remember it from Algebra 1. How do I find the slope or average rate of change? Average rate of change equals slope. There we go. Put that there. That equals the slope. That is an O. This is the same thing. Average rate of change equals slope. So if you don't have that formula memorized, then you need that in your notes when you get to that average rate of change problem that we're going to have. All right, let's go back. Average rate of change. There's that formula, m equals y2 minus y1 over x2 minus x1. So they have some examples there that you can look at in our lesson. All right, so he shows how to graph an arithmetic sequence, and he does it by hand. We've already looked at it in Desmos, so I'm not going to watch this video, but you can watch the video if you need to, if you want to go back and see that. But we've done that on Desmos, showing you how to do that right up here. All right. Explicit arithmetic sequence, and this is showing how to graph this arithmetic sequence, which you could put that into Desmos. So what he did is he took A1 plus DN minus 1 and substituted. He got 3 replies for his birthday on the first day. He got 5 more the second day. So the second day he got 8 replies. Then he got 13 replies, and he got 18 replies. And you can just put this formula. You don't have to simplify it. They simplify. You can put it just like this, and it would graph it. So let's see. 3 plus 5 n minus 1. 3 plus 5, and we do x minus 1 since it's on Desmos. And there it is. There is, he got 3 replies to his birthday the first day, then 8, then 13, then 18, then 23, then 28. Just put in the arithmetic sequence formula and let Desmos graph it. See, there's their graph. Looks just like our graph. All right, and geometric, same thing. Just put the formula in, and it will graph it. This one's the one that goes down, so decay. All right, so page 4 has our summary. There's the 2 formulas again that you should already have in your notes with more examples. But the lesson summary just talks about graphing, restrictions to the range and domain. Remember, domain is greater or equal to 1. Notice when it graphs it, not the equation here, it starts at 1. It doesn't graph anything at 0 or the negatives. Desmos knows that when you graph a sequence like this, you have to start at 1 because we told it we're limited to 1 to 8. Because we know that we're limited starting at 1. We can't have a 0th term. So Desmos just graphs what we tell it. All right. The graphs are discrete, meaning they're not connected. They're not continuous because it's only valid at specific points. There's the formulas for graphing sequences, graphing series, and the average rate of change formula. So let's look at the lesson that goes with the assignment that goes with this lesson. Oh, look at there. The very first one, calculate the average rate of change. The rate of change. Another average rate of change. This one's arithmetic. This one's geometric. Graph the first 6 terms. They give you the first term and the common difference. So you can do that on Desmos and compare, or you can look at this to see if that is actually correct. The first thing I would say is you know what the very first term should be. A1 equals 3. A1 equals 3. So You should be able to do that without graphing on Desmos, because this one says the first term is -10. Starts at -10. It can't be right because you know the first term is 3. So that should give you a big hit right away, which graphs you can eliminate because it doesn't have the first term as 3. -10. That's just silly. Here's another one. First term is 2. The ratio is 4, so it goes up times 4 every time. So what do they have? That's a little harder to tell if it's at 2 or not, but they give you the points right here. 1, 2, 2, 8. So they give you the points. All right, graph these 6 terms of a finite sequence where A1 is 5 and the ratio is 1.25. So which one of those graphs would do that? It uses that ratio. It goes up by 1.25 each time, starts at 5. All right, that's it. Just 5 problems, and most of them are matching the graph to the problem there. That's all we have for this week. Remember, we're not going to do that sigma notation thing, so I'll get rid of that. But all right, if you got any questions, hang around. Otherwise, go forth and complete algebra. And I should have all the grades updated for your grade check today. So see ya.